Greetings everyone, my name is Minglu. I'm here to share our work on evaluating the reliability of over 1.8 million NVMe SSD deployed at Alibaba. This is a joint work of researchers from Shanghai Jiao University, Xiamen University, in a cooperation with Alibaba Group. Hardware failures are one of the major hurdles to maintaining service reliability. It is crucial to understand the reliability of hardware in the cloud. In this study, we focus on studying the reliability of storage devices. Over the last decade, the storage landscape has changed. Data centers are widely adopting flash-based SSDs instead of hard drives. In recent years, there are several works investigating SSD reliability. For example, they study the impact of SSD internals, failure rate curves, and correlated failures. However, the SSDs they focused on are early generations with a SAS or SATA interface. Nowadays, we clearly have more options for storage devices. NVMe SSD has been on the market for several years. With gigabytes per second level bandwidth and microsecond level latency, NVMe SSD is widely adopted in today's data centers. Compared to early SSDs, NVMe SSD is not just a simple interface upgrade. Many recent changes in reliability have been well integrated. For example, the wide adoption of 3D NAND flash, ring protection, and LDPC coding. With such considerable changes, the reliability of NVMe SSD remains unknown. In our work, we conduct two failure studies. First, we provide a comparative fail-stop study. We start with existing findings and examine whether such findings persist in NVMe SSD. Second, we conduct a quantitative fail-slow study. We identify fail-slow failures as a widespread and severe problem in NVMe SSD. We investigate the impact factors and the fail-slow to fail-stop transition. Next, I will introduce our dataset. Our dataset consists of over 1.8 million NVMe SSD deployed at Alibaba data centers. All of them are enterprise level. The SSD fleet covers various drive specifications, with a diverse mix of drive age and usage. A total of 7 cloud services are served by these SSDs. We collect device-level data covering the smart logs, failure tickets, and performance logs. These data are collected from the device, monitoring daemons, and IOStat command. All our datasets are released in public now for open access. We hope to inspire researchers to conduct valuable studies that benefit the community. We begin our study by considering the fail-stop failures. To understand when storage devices fail, we first take a look at the failure curve. The first question is, how do failure rates vary as the device gets older and more worn out? There are already answers for hard drives 15 years ago. At infant stage, that is, upon the first few months of deployment, the failure rates are notably high. This is known as the infant mortality for hard drives. Then, in 2015, researchers examined the failure curve of SSDs in Facebook. They discovered that SSD would experience a rise in failure rates at an early age, before the infant mortality arrives. In 2020, researchers examined the failure curve of SAS and SATA SSDs in NetApp. Similarly, they discovered that infant mortality could extend to more than a year. During the infant stage, the failure rate could be 2 to 3 times larger than later in life. To sum up, previous studies point out that flash-based SSDs would experience a drawn-out period of infant mortality. So what about an NVMe SSD? Here's one example. As we can see, the failure rates oscillate around the average values across time. Also, during the first few months, the failure rates are not notably high compared to later in time. We have examined the failure curves of 6 major NVMe SSD models in our dataset. all of them do not have outstanding infant mortality during early periods. In particular, the failure rates in the first 3 months are equivalent to or even lower than the later periods. In later periods, failure rates still oscillate around the average values and is not notably high. This indicates that even in later periods, by up to 40 months of deploying, NVMe SSD still does not reach wear-out period. Let's go back to infant mortality. According to previous studies, infant mortality is notable in SAS and SATA SSDs. In this sense, we are interested in why it is the case for NVMe SSD. We examine the smart attributes during the first 15 months of deployment. Note that these two figures in the slide are from the same drive model for straight comparison. Smart logs record device-level errors. As we can see, the device errors are notably high at infant stage, and then gradually decrease to a much lower value. In other words, drives still produce and accumulate much more internal errors at infant stage. So why the corresponding failure rates are still mild and not notable, while on the other hand, the failure rates in SAS and SATA SSD are non-negligible. We assume that this is likely due to the recent improvement in FTL error handling. The FTL may tolerate and mask errors, so that drives will still be functioning with considerable errors. Therefore, we do not see high failure rates during the early deployment of NVMe SSDs. In previous practice, to tackle infant mortality, cloud operators usually have to stockpile extra pieces before initial deployment, so that they can replace failed drives in time during early deployment. Since the infant mortality in NVMe SSD is not notable, it is unnecessary to stockpile extra pieces now. This can serve as a relief signal for supply chain as well as system administrators. We also investigate how write amplification affects SSD reliability. Write amplification is usually attributed to SSD internal operations, like GC, for example. The corresponding write amplification factor is calculated by dividing the amount of NAND writes by logical writes. Usually, write amplification factor is above 1. In some cases, where the writes are compressed, it could be less than 1. Previously, researchers from Microsoft divide their SSDs into WAF buckets and calculate the failure rates. As we can see, failure rates are high at both ends, meaning that the SATA SSD would experience high failure rates at both low and high WAF levels. Also, for WAF above 1, the failure rates seem to increase as WAF increases. So what about in NVMe SSD? Following the same methodology, we examine the failure rates at different WAF levels. First, when WAF is below 1, the failure rate is still obviously high, which is 2.19 times higher than the average of all bars. Second, NVMe SSD becomes more robust to high write amplification. This indicates that NVMe SSD is less affected by random small writes, which is a major cause of high write amplification. Such a trend persists even after we exclude the influence of workloads and drive usage. Recall that data compression could lead to a less than 1 WAF. We further check the WAF distribution of our NVMe SSD fleet. In fact, extremely low WAF is rare in our case. Only 3.3% of NVMe SSDs are experiencing a less than 1 WAF. Therefore, for NVMe SSDs, low WAF levels are still rare but deadly, while high WAF levels do not come with high failure rates. In previous practice, system software developers focus on reducing SSD write amplification. Recall that in NVMe SSD, high write amplification does not necessarily mean a high failure rate. Therefore, the design vision and design goal of developing systems with low write amplification support may be shifted. Lastly, we investigate the correlated failures. correlated failures are notorious in distributed systems. For example, multiple independent components could fail within a short time, posing a significant threat to system availability. Therefore, it is important to understand the distribution of correlated failures in SSDs. Failures could be both spatially and temporally correlated. For example, correlated failures could arrive at the same node within a few minutes in sequence. Previously, researchers from Alibaba analyzed the correlated failures in SATA SSD. First, they divide SSD failures that occur at the same geographical locations into intranode and intra-rank failures. Then, based on the arrival time, they are interested in failures that arrive within a certain time interval. For example, from 0 to 1 minute or from 1 day to 1 month. Here is an illustration of their correlated failure distribution. Obviously, in nearly all models, intranode and intra-rank failures mostly arrive within 1 minute, and thus, spatially correlated failures are temporally correlated in a short span. So what about an NVMe SSD? Following the same methodology, we analyze the distribution of correlated failures in NVMe SSD. Here's an example showing the intranode failure distribution. The trend is similar for intra-rank failures, so they are not shown here. We make two observations here. First, let's focus on short-term failures by looking at the red bars. Recall that short-term failures are dominant in SATA SSD. However, in NVMe SSD, such failures are no longer prevalent within 1 minute. In some models, they are even negligible. On the contrary, long-term correlated failures between 1 day and 1 month become notably frequent. Although in SATA SSD, long-term correlated failures are almost negligible, they become the dominant ones in NVMe SSD now. In practice, the decline in short-term correlated failures could generally imply a lower risk of system-wide failures. However, at least in our data centers, we usually start with software-based approaches when fixing drive failures, like data scrubbing or file system checkers. As a general approach, such online checking and repairing could take time. So we further check the repair time recorded in the failure tickets. As a result, around 43.9% of drive failures take more than a day to repair. Based on our findings, we have refined our operation process. Now, we directly put drives offline upon failures. In this case, we can reduce the chances of suffering from long-term correlated failures. Despite fail-stop failures, we also conduct a quantitative fail-slow failure study in NVMe SSD. Fail-stop drives are already reported in failure tickets, but what about fail-slow drives? How to identify them? There are two major challenges. First, there's no ground truth in identifying fail-slow. Unlike fail-stop failures, where the oracle is clear, there are 1,000 ways to define fail-slow. For example, on-site engineers are often confused and ask how slow is a drive to be considered fail-slow, and the answers may vary across different people. Maybe when the I/O latency is above 100 microseconds, maybe sometimes about 500, or to be even more strict, about 1 millisecond. The second challenge is that the underlying root causes are hard to tell. With no off-the-peg answers, there are many aspects that could cause performance degradation. For example, by hardware failures like the fail-slow, or by a temporarily heavy web workload, or by a one-shot high GC time. To identify the fail-slow, we make use of the latency time series collected by the monitoring daemons. Here's one example showing the latency time series of 12 drives from the same node. Clearly, there's one drive suffering from a period of slowdown. Therefore, the first step is to identify any suspicious drives with abnormally high latency. To do so, we first calculate a statistical bond. If a drive has higher latencies than this bond for more than half of the time, we then mark this drive as suspect of fail-slow. Other drives from the same node are referred to as peer drives. We also place a similar upper bound on the throughput and IOPS time series. In this case, we could filter out performance degradation caused by heavy workloads. The second step is to identify the slowdown events. Here, by peer evaluation, we compare the suspicious fail-slow drive with its normal peers. Specifically, we place a sliding window along the temporal dimension, incorporating consecutive slow records into slowdown events. Intuitively, a slowdown event should last longer than the sliding window size. In fact, we set 4 values for the sliding window length, varying from 5 minutes to 60 minutes long. Since normal GC usually takes less than a few seconds, a sliding window of several to dozens of minutes long is enough to filter out the side effects brought by normal GC. We hypothesized that the ultra-low latency nature of NVMe SSD could make itself prone to fail-slow failures. For strict comparison, we also identified the fail-slow failures in hard drives, and the results are clear. Fail-slow failure is a widespread concern for NVMe SSD. Those figures show that NVMe SSD could be dozens of times more likely to suffer from fail-slow failures than hard drives. We also take a look at the severity of fail-slow. Clearly, the average latency of slowdown events in most NVMe SSD models are already hundreds of microseconds. This indicates that fail-slow NVMe SSD could degrade to SATA SSD level performance. Moreover, we checked the top 1% slowest event. Surprisingly, a small fraction of NVMe SSD even degrades to HDD level performance, and the latency of these slowest events reaches an average latency of over 11 milliseconds. Therefore, fail-slow failure is also a severe problem for NVMe SSD. We also take a look at the transition from fail-slow to fail-stop. We collect up-to-date failure tickets. The latest one is 5 months older than the last recorded slowdown event. And we are interested in whether any fail-stop drives are fail-slowed in the first place, which corresponds to the intersection of fail-stop and fail-slow drives. In fact, there are only 10 drives transit from fail-slow to fail-stop, accounting for less than 0.01%. Thus, the transition from fail-slow to fail-stop is rarely observed. We also have examined the fail-slow event reoccurrences, identified several fail-slow impact factors, and investigated the correlation with smart attributes. And for the conclusions, by drawing side-by-side comparisons with existing reliability studies over SAS and SATA SSDs, we have identified 3 major reliability changes in NVMe SSD. First, infant mortality is not notable. Second, extremely low write amplification is still rare but deadly, while higher write amplification is not a big concern. Third, spatially correlated failures are temporarily correlated only in the long-term span. Short-term correlated failures become much less frequent. Moreover, we conduct the first large-scale study on fail-slow failures in storage devices. We identify fail-slow failure as a widespread and severe problem for NVMe SSDs. We investigate the impact factors of fail-slow failures. We show through statistic tests that hardware errors in smart attributes are not good indicators of fail-slow. Lastly, we confirm that the transition from fail-slow to fail-stop is rarely observed, at least not in a short interval of 5 months. Thanks for listening. If you have any questions, feel free to contact us via the email at the bottom.